Hey everyone, welcome to the Joy of Coding at Portland State University. Object-oriented programming aims to create software that is easy to work with so that many people can contribute to its evolution over its lifetime. A key challenge to effective object design is appropriately decoupling objects that interact with each other. Well-structured objects obey the single responsibility principle that states that an object should do only one thing and do it well. The dependency injection design pattern encourages object structures and implementations that make the separation of responsibilities clear. Moreover, the dependency injection pattern removes the burden of managing dependent objects from the objects that depend on them. This enables sophisticated object management techniques like singletons and factories. Additionally, it enables tests to manage dependencies as mock objects that can provide the desired behavior without an expensive or complex implementation. Let's dive in. So in this screencast, we're going to talk about two topics related to testing with mock objects. First, we'll get an introduction to the dependency injection design pattern, and then we'll talk about the Mockito library, which provides a fluent API for creating and working with mock objects. To begin with, let's talk about objects and how they depend on each other. The next couple of slides are going to talk about a series of objects that exist within a bookstore application that uses classes from this hierarchy. There's a bookstore class that allows a user to purchase and refund books using a credit card. Instances of this bookstore class depend on other kinds of objects, such as a book inventory, which keeps track of what books are available, and a credit card service that processes the credit card transactions. Now, this code has already been pretty well factored out in that the bookstore depends on an interface that specifies the behavior of something like a book inventory or a credit card service. And that interface is then implemented by classes like book database, which implements the book inventory and stores the inventory to a file. Similarly, the credit card service interacts with a REST API provided by the First Bank of PSU. And that REST API has a hostname and a port that it runs on. This is a good example of programming to the interface. The bookstore can just call these interface methods and not have to worry so much about the implementation. This makes it easier for us to provide different implementations of book inventory and credit card service without having much impact on the code in the bookstore itself. So given that object design, how can we implement these classes? Well, let's take a look at bookstore. Like we said, bookstore has a field of type book inventory, the interface that it's programming to. Same thing for credit card service. But let's look at the constructor for bookstore. So bookstore needs to initialize these fields. And notice that both of these fields are final because those values are only set in the constructor. Once a bookstore has established what its book inventory is, it doesn't need to change it. So when we create a bookstore, we need to create the book inventory and credit card service. So the book inventory is going to be an instance of book database. Book database needs to know what directory it's writing the file to and the name of the file in that directory, so we provide that there. And similarly, when we create the credit card service, we instantiate a class of First Bank of PSU, which is a client to the REST API that is hosted at localhost, we'll say for ease of simplicity, on port 880. The important thing to note here is that when the bookstore is created, it also creates its dependencies. Now let's look at the implementation of the purchase method in the bookstore. We purchase some number of books using a credit card. This is a purposefully simple implementation of this code just for demonstration purposes. So we iterate all of the books that we want to purchase, remove them from the inventory, and keep track of the total price of the books that we purchased. Once we have the total purchase price, we're going to debit it from the credit card by calling the debit method of the credit card service using the card that was passed in. If the debit transaction was successful, then we'll return the total. Otherwise, we'll throw an exception. So here, note that the purchase method uses the dependencies, but it programs to the interface, right? It calls getPrice, it calls debit. These are the abstract methods on the interface, not necessarily the methods of implementation. This is good code. But there's some things about this code that it could be better. The first one I want to call out is that it's really difficult to test this code, because when you create that bookstore object, you can only create it using, the actual database, which might be slow, and then the real credit card service, which probably costs money in transactions, right? You don't want to be exercising these APIs often because it costs time and money. Also requires a lot of data setup, right? You'll need to create the database file and create an account with the credit card processing code. And because of this code is hard to test. As we saw in the constructor for bookstore, the bookstore object has to know how to configure its dependencies. And you have to ask yourself, does the bookstore really care what port the credit card service runs on or what file the book inventory ends up using? Additionally, if other code wants to use the book database, it would have to create another instance of it, or you'd have to have some code that maintains a global instance of it, because two book databases can't work on the same file. And if we want to change to another implementation of the dependencies, let's say there's a different credit card processor that you want to use or a different kind of book inventory database, you have to change the bookstore object itself. And this doesn't seem decoupled, this doesn't seem clean. Again, so it really begs the question, does the bookstore really need to care what kind of book inventory it uses? So this ended up being a pretty common problem with object-oriented code. You end up with code that's tightly coupled, which makes it hard to test and harder to evolve. At some point, the so-called Hollywood principle was coined, which states that dependent code should require that its dependencies are provided to it instead of creating those dependencies itself. It's called the Hollywood principle because the idea is like, hey, don't call us, we'll call you. Meaning that someone else will provide me the dependencies, me being a class like the bookstore, instead of me having to create them themselves. What this means in practical terms is that dependencies are provided to an object via its constructor instead of that object creating it itself. So to apply the Hollywood principle to the bookstore, well, we simply provide the book inventory and the credit card service to the bookstore object. We simply store them in the fields. The constructor for bookstore now doesn't need to have any knowledge about what particular instance of book inventory or credit card service to create. Now, of course, someone will have to create these objects, and so, hey, let's say it's the main method of the app that manages the bookstore. Yes, it will have to create these instances, things like the particular book database or the connection to First Bank of PSU, and then ultimately create the bookstore, and then provide that to the code that takes input from the user, etc., etc. So now that we've got a bookstore that knows nothing about its dependencies, only knows what interface they implement, it makes the code a lot easier to test because now we don't need to provide actual production level instances of book inventory and credit card service. We can instead provide objects that behave like a book inventory or a credit card service, but don't necessarily need to do all the same work of the actual production ones. Because what we're looking to test is the behavior of the bookstore object, not of its dependent objects. So how might one implement these so-called mock objects for mocking out the behavior of book inventory and credit card service? Well, when it comes to testing your code, you want to be really clear about your expectations. And so oftentimes, if there's a method that's called that you don't expect to be called, you want to know about it. You want your test to fail because you're surprised by it. So an important part of mocking objects is throwing exceptions on things that shouldn't be invoked. So we have a superclass of our mock objects called mockObject, and it has one method. It's called shouldNotInvoke, and it's protected, and all it does is throw an exception. And we'll use this shouldNotInvoke method in our implementations of our mock interfaces. So here's an example of a mock book inventory. It extends a mock object, and it implements book inventory. Because it implements book inventory and the class is not abstract, it needs to provide implementations of all the methods, like the remove method. Now, by default, again, mock objects, unless you've told it to do otherwise, should complain about the interactions with it so that you can detect surprising or unexpected interactions. So the remove method simply invokes shouldNotInvoke. So now we have these mock objects that implement our interfaces on which the bookstore depends. And when we want to use those objects in a test, those mock objects in a test, we need to override the expected methods to keep track of how they were interacted with. So here's an example from a class called bookstoreTest. We test if a book is purchased. So what we want to do is we want to make sure that when a book is purchased, that is actually removed from the inventory, meaning that the bookstore object invokes the remove method with the book that we expect. So in order to keep track of what book is actually removed from the book inventory, we create an anonymous subclass of mock book inventory that overrides the remove method to basically store the book that was sent to it off in an array so that we can access it later. Furthermore, for this test, we want to make sure that when the debit method is invoked, it always returns success. Doesn't matter what credit card, doesn't matter what amount. For this test, all we're doing is making sure that the book is removed from the inventory. So our credit card service, well, we want to be pretty simple. Any transaction is successful. So we've created those two mock objects to provide the functionality that we want from our book inventory and our credit card service. And now we're going to use them in the test code. So we'll create a bookstore object that uses that mock inventory and that mock card service, and then we'll interact with it. We'll create a credit card, we'll create a book. We will then invoke the purchase method on the bookstore. Now this is the code that's under test. We'll send it the book and we'll send it the card. Now, if you remember from the implementation of purchase, we really haven't changed that very much. It uses the book inventory and the credit card service. And in this particular test, it's interacting with those mock objects that were passed in. Now, the purchase method doesn't know that it's interacting with mock objects, and it doesn't care, right? They implement the interface. It's just going to invoke methods like removing the book. So we invoke the purchase method, and we get the total. We want to assert that the total of books purchased was equal to the price of the book. We use the assert equals method from the JUnit API. I don't know if you've seen this one or not, so I'm going to explain what this assert equals does. It asserts that two doubles are the same, but it takes three parameters. So the first double is the expected value. The second argument is the actual value. And then the third value is the tolerance. How close are the two double values? Because you can have round off error and things like that. In this case, because everything's a nice round number, we're just going to say a tolerance of 0. So now we've invoked our method that does the work. We've verified that it returns the right value. But what we're also testing here is that the book that we purchased is removed from the inventory. Well, how do you do that? Well, now we're going to interact with the mock object, and actually we're going to interact with the side effects of the mock object, which, as you may recall from the previous slide, was to take the book that was removed and store it into that removed book array. We're going to get the first element of the removed book array. We're going to make sure that it's not null, and then we're going to make sure that it is the book that we expect by comparing the title, author, and price of the removed object to the test book. So mock objects get the job done, but this style of mock objects is really awkward to work with. Right, we had to write a lot of code in order to mock out these interfaces. And this is just code you need to maintain. So when something about the interface changes, we add a new method, we change the signature, and we also need to change the mock implementations of it. And then look at how hard it made the code to read. Right? We had to use anonymous subclasses, we had to keep track of what state was passed into the dependency. Again, gets the job done, but it's super awkward. A lot of people got together and said, there's got to be a better way of doing this, right? And so they did what software developers often do, which is to create a library. And there are several libraries out there for the Java programming language that allow you to easily create mock objects and then be able to leverage the dependency injection pattern in your code to make easy tests for complex code. We're going to learn about one of them called Mockito, which can be found at that website. What Mockito gives you is a very rich API, a Java API, for creating these mock objects, for configuring them to have the behaviors that you want, and then assessing the interactions that the code under test has with those mock objects. It provides what's called a domain-specific language, or DSL, for creating the mock objects and configuring them the way that you want. And you can also specify the behavior, or I think of them as sort of programming the mock objects to behave in the way that you want. And we'll see examples of this shortly. In order to leverage this library, you need to add the Mockito core artifact to your pom.xml. And so you'll see code like this in pom.xml, where you specify, well, the group and artifact for Mockito, the particular version. And then because Mockito is only used in test, you say that the scope of Mockito for the dependency is test scope. And that way, the Mockito library won't be included with your production code. So here's how we could write a similar test, the one we just saw, for verifying that the purchase method of the bookstore class interacts with a Mockito managed mock credit card service in the way that we expect. So we start out by creating a book and specifying that the price of the book is $1. We use the Mockito API to create this object and configure this object. I don't know if this is what you really want to do in the real world, but this is just for an example. Mockito provides a method called mock, which creates a mock instance of a particular interface or class. So in that first line, we create a mock book. Mockito also contains a method called when, that specifies that when the getPrice method is invoked on that particular book, on that mock book, then that method should return the price that we specify here in our test. We're also going to mock out our book inventory and our credit card service. And we're going to use that when method again to say when the debit method is invoked on the credit card service with any credit card instance and any double value, then it's going to return a success code. Then we're going to create our code under test. Here we're going to invoke the constructor of our bookstore with the Mockito managed mock inventory and the mock credit card service. So here it's important to point out that the bookstore is the actual code. The bookstore itself isn't mocked. This is the real code that we want to invoke, but we pass it mock objects that it interacts with. Then we're going to create a mock credit card, and we're going to call a purchase method by sending it the mock book and the mock credit card. And the purchase method will execute as it normally does, again, interacting with these mock objects. It doesn't care that the book that's passed in, or the credit card that's passed in, or the book inventory, or the credit card service are all mock objects. It just invokes the methods on them, and the mock objects return the behavior that the test wants. Again, we're going to assert that the total amount of the purchase is the purchase price of the one book. And then the last line of the test uses the verify method of the Mockito API to verify that the debit method of the card service, of the credit card, of the mocked credit card service, was invoked with the card and the price that I expect. And that last line is really what the test is validating. It's validating that the credit card service was charged the expected amount. There's a lot here, so let's take a closer look at all these pieces parts of the Mockito API. The primary class that you interact with in the Mockito API is the Mockito class and the org Mockito package. In the examples here, we've used the static import in Java so that we can just call a method like when or mock without having to prefix it with mockito.when or mockito.mock. The mock method creates one of these mock objects for some interface or some class, and it takes an instance of the class of the book.class object as the class to mock. And that returns an instance of that class or an instance of that interface that then is recognized by the Mockito API. Now this mock object out of the box doesn't know how to do anything. It doesn't know how to provide an implementation of all of its methods. So if you were to attempt to invoke a method of a mocked object that hadn't been programmed otherwise, it'll return a no-op if it's void, or return a null or a zero value if it has a return value. Now, this is really cool and really advanced stuff. If you look at how it's actually implemented, it uses dynamically created classes at runtime. It uses something called the reflection API to do all really cool stuff. And those are really topics that are beyond the scope of this course. But what I would like you to have an appreciation for is the fact that you can do this rather advanced mocking with the Mockito API using the Java platform. So recall from the previous example that most of the objects that we created, except for the bookstore, that was a real code, all the other objects were mocks. This meant that we didn't need to invoke constructors directly, and we only needed to specify the state and the behavior that we needed for the test. Everything else, who cares, is not going to be used. So for instance, this test, it doesn't really matter what the title or the author of the book is, and so why even provide those, right? That just adds cognitive load to the test. It also means that as our objects evolve, as more methods are added, or if certain methods are changed, this code isn't impacted. Because Mockito hides those implementations, and if you're not going to invoke a method whose signature ends up changing, why should you have to update your code? So the mock method creates one of these mock objects, and then there's the when method, which specifies the behavior that the mock object should have. So if you look at the signature of the when method, it takes an object of some type t and returns an object with the kind of awkward name of ongoing stubbing of type t, you then interact with by invoking other methods in this Fluent API. Now, note that if you're mocking an object that has final methods, which interfaces won't have, but you also mock an object. So if there's a final method, you can't use the when with final methods because, well, they can't be overridden. Behind the scenes, Mockito does a lot with overriding methods in order to provide the bookkeeping that it does. So after you've invoked when, it returns this object that's called ongoing stubbing, and it provides methods that specify what behavior the mock object should have when that method is invoked. So we saw this in the previous example. You can invoke then return to have the mock object return a particular value when that mock method is invoked. You can also specify that when that mock method is invoked, an exception should be thrown by calling then throw on the thing returned by the when. If you're mocking a class, you can also have the mock object call the real method, which might be appropriate in some cases. Syntactically, we usually chain the calls together, so you have something that reads maybe a little bit more naturally. So you say, when book.getPrice is invoked, then return the price that we use in our tests. The when method in the Mockito API also allows you to specify different behaviors for a method depending on what parameters are passed in. So for instance, we can use multiple calls to when to specify that when the debit method is invoked with a particular card and price, then that should be successful. We can also specify to say that when debit is invoked on a particular card with a price of -1, then that debit method should return invalid amount. Something we saw in the code example is that sometimes we want the behavior of the mock method to do the same thing regardless of what value is passed in its arguments. So for instance, always return success no matter which credit card is passed in. As you may recall, we did that by using a method called any from the Mockito API. We basically said that when the debit method is invoked with any instance of credit card and any price, then it should return success. There are a number of variations on the any method in Mockito. There's a zero argument any method that will match any object or a null object. There's also the any that we saw, which takes a class, which will match any object of a given type. There are also any methods for the primitive types, like any int and any double, and also any string for convenience. There are also matchers for null values, for matching not null value, and matching the same value as a particular object, as well as matching a regular expression for a string argument. Now, one of the things about the Mockito API that I know I'm always running into is that if you're going to use a matcher, like any, for one of the arguments to the method that you're mocking out, then all arguments must be matchers, just the way it works. So in this case, if we want to specify that when the debit method of the credit card service is invoked with any credit card and a value of -1, then it should return invalid amount. And the matchers that we use are, well, for any credit card. But then you just can't say -1. You need to use the EQ, the equals matcher, for the value -1. Matchers are a really important and powerful part of the Mockito API. And there's a class called additional matchers that gives you even more of them. You can combine matchers using Boolean operations. So you can say, yep, match anything that is greater than 0 and divisible by 5. So we've seen how to create a mock object with the mock method. We've seen how to configure the behavior of a mock object with the when method. And so once you've got your mock objects all configured, you send them to the code under test. The code under test interacts with them. And then you can verify that the mock objects were interacted with in the way that you expect. You use the verify method for that. The Mockito managed mock objects will keep this history, if you will, of what methods were invoked and what arguments were passed in. And so then the verify method lets you assert, for lack of a better word, that a mocked method was interacted with in the way that you expect. So here we can say that, yes, verify that the card service had its debit method invoked with the specific card and price that we expected. You can also use matchers with the verify. So you can say, verify the card service, its debit method, was invoked with the same card that we expect, with the price equaling the price that we expected. And of course, here you can use other matchers like the regex matcher or a greater than or less than matcher. So that's an introduction to dependency injection and working with Mockito managed mock objects. I think of dependency injection as being the ultimate expression of programming to the interface. Here we really see how that principle of not caring about the implementation can be put into practice. So then as you're designing your objects and how they interact with each other, think about how to apply the Hollywood principle so that objects receive their dependencies when they're constructed as opposed to having to construct them themselves. If you do this and you end up with dependencies that are decoupled, you can enable a finer grained testing that is easier and cheaper to do because you're not using the real objects. And one way to implement those tests is to use an API like Mockito, which provides rather advanced facilities for creating, configuring, and verifying mock objects. And that's it. I hope you enjoyed learning about dependency injection and testing with Mockito. If you're feeling a little confused or overwhelmed, it's okay. You can always go back and watch the screencast again, because dependency injection and Mockito are certainly two of the more advanced topics in the joy of coding here at Portland State University.